Welcome to Hot Topics. In this video, we're going to go over the principles of grounding, and we're going to tie it to the 2023 NEC as well as the 2020 NEC. So now, reviewing this, we want to look at the supply side. In the illustration, that's 250.102C. And you know, from our experience as engineers, electricians, inspectors, and so forth, supply side, there's not an overcurrent device ahead of your conductors. The load side now, you have an overcurrent device ahead of your conductors. So you're looking at 250.102C for supply side and 250.102D as in dog for the load side. Now you notice to the left of the illustration at the top, we pick up utility ground. And that's defined in the National Electrical Safety Code Rule 091 as well as 092. And the utility in the National Electrical Safety Code basically say that when we bond and ground our supply, we're not grounding the service. You have to go to the service equipment and ground it in accordance with your 250.130A and 250.24A. So we're going to have two grounds, one at the service and one at the utility transformer side, whatever the supply is. And then you notice that there's a rule of thumb that electricians have used for many, many years as well as engineers, that if they had a 350 amp main, as you see in the illustration, they would just take that 350 amp main and multiply it by 189, as you see in the green illustration here. When I say green, it's the green typing. And when you multiply 350 by 189, you come up with 66,150 circular mil. Now you can just look at Table 8 to Chapter 9, and that would require a number 2 copper conductor. That's good for 66,360 circular mil, which is fully capable of handling 66,150, as you see calculated in green there. Now, you always would use your table 250.102C1 if you're sizing this grounded conductors you see on the service equipment here where the 350 amp main is. Notice that you would go to your table 250.102C1, and if you had, say, 350 kc mil conductors terminating to 350 amp main, Table 250.102C1 that you see here in red, supply side, would require a number 2 grounded conductor. But now when you calculate the neutral calculation, if you had neutral load, in the red here to the right, 220.61, and you calculated a 1/0 neutral, then you would use 1/0 here. Now, I believe it's 408.4, you get into circuit mapping. And it basically, you know, you look at your circuit mapping, and if you're just, your panel board is just loaded up with neutral loads, then this calculation here usually produces the largest conductor. But if your, you know, your circuit mapping label indicates now you have a lot more phase-to-phase loads than neutral loads, then this table 250.102C1 would produce the largest because it would be number 2, see, for 350 kc mil. But if you calculated, say, a 1/0 or a 2/0 in 220.61, then this size, calculating the neutral, would override it. But the good rule of thumb, see, is to review your circuit labeling and see if that, if the panel is loaded up with neutral loads or phase-to-phase loads without neutral. So keep that in mind. And then, of course, the grounding electrode conductor, You size everything from table 250.66, and usually that's building steel or water pipe. And then you would go to 250.66A through 3 to do the sizing of your grounding electrode conductor. And notice this is a load side. You have an overcurrent device ahead of these conductors, routed over to this panel board in the building 2. Here you have a feeder routed into the same building, and you have a separately derived system. You're tapping off the secondary side of it, 240.21C usually, and you can see that there's no overcurrent device ahead of these conductors, so that's considered supply. Now, notice one thing when we went over and reviewed table 250.102, C1. If you had 350 case mil that you see here in the boxed in table, number 2. Now, what did we calculate? Well, we took the 350 amp main times 189. This always works. We come up with 66,150 circular mil, remember? That would require a number 2 in accordance with table 8 to chapter 9, because we would come up with approximately at 66,360. That 3 shouldn't be there. We would be okay, see. Now, this is a rule of thumb method that we would use for the supply side, meaning what? There's no overcurrent device ahead of your conductors. Now, the next illustration is equipment grounding and bonding, see? And that's 250.4A2, A3, and A4, and 250.4. And notice equipment ground made up good and tight, as required by code. 10% of a fault current will travel over your equipment ground if now your conduit couplings and connectors are all made up tight. You don't have a bunch of punched out rings loose and that kind of thing. 90% of your fault will travel over that metal conduit. Now, we know we find this in the IEEE Green Book that IEEE puts out. You can also find it in Soares' grounding book. And then the rule of thumb that we always use in the field, because we didn't have maybe a lot of this information available to us, if the overcurrent device in the panel board, as you see here, was over 400 amps, it's 25% of the overcurrent device. Equipment ground should be that large. If it's, say, 400 amps or less, and we just usually, good rule of thumb, 50% of the overcurrent device. And we know we would have an equipment ground large enough that if you developed a short circuit current, as you see at the equipment, you would have installed an equipment ground large enough to return the available short circuit current back to where the bar is earth grounded and then routed back to the transformer, which is earth grounded. Now, another rule of thumb that we would use, the branch circuit with a 100 amp overcurrent device, the multiplier would be 131. 131 times 100 would be 13,100 circular mil, and you went to table 8 to chapter 9, that would be a number 8 that we would use. Now, keeping that in mind, and we'll move to our next illustration, then notice at the right-hand side in the green typing, a multiplier is used when you're 40 amp overcurrent device or less. You're up to 40 amps or less. 15 to 40 amps, then you would use 260. 260 times your overcurrent device then would give you your circular mil rating. For example, 15 to 90 amp, you'd use 115%. Times your overcurrent device, and that would give you your circular mil rating. So look at this note now. We have a 40 amp circuit breaker, as you see in the illustration here, times 260 because we fall within the multiplier for up to 40 amps, 10,400. Now we go to table 8 to chapter 9. Now in your 2020 code, maybe it's a better way to say that, that'd be page around 705, I believe. And you pick up 10,000 400 amp circular mill would require a number 10. And remember, you're rounding up every time. Now, if you had a 100 amp overcurrent device, a greater than that, then you would use 131 times the overcurrent device. For example, we have a 100 amp overcurrent device times 131, 13,100. Go to Table 8 to Chapter 9, page 705 of the 2020 NEC. Number 8 would be required. So we're using the Table 8 to Chapter 9 after we determine a circular mill rating based upon the multiplier, based upon these size devices that you see listed there. Now, for example, you have a 100 amp overcurrent device right here. This is table 250.122 on page 133, I believe it is in your code book, 2020. 100 amp, number 8. Well, now, wasn't that just exactly what we calculated here? We took that 100 amp overcurrent device times that multiplier, 13,100. Yes, it would require number 8 when we go with this table to get the circular mill rating that would derive our equipment ground size. And these are the values you look at, see. You're either 15 amp up to 40, or you're over 40, see, up to 100. And you can see where you would pick this up, 40 amp there, 260, see. So once though you get above that and you get 100 more, it's 131, see. So keep that in mind, and then notice it's verified right here. It'll work for you. But again, if you have your code book handy and wiggy, just use the table. You don't have to do any of this. But I had, in my career, it didn't matter from an engineering point of view or electrician's point of view, maintenance point of view, whatever we may be doing, I always just took the main, because that's how I was taught. And whatever the main is, multiply 189, and that's the minimum size grounded conductor that you need to return the short circuit current during a ground fault condition. Now, moving to this illustration here, then say you have a bonding jumper here to service. You should read not less than 1.1 volt. AC should be read here to have a real good size bonding means if you're using a conductor. Now you're going downstream to here. Downstream to the panel board you see to the left there. And then downstream, a reading of an excess of 3 volts or less than 0.5 volt AC indicates you got a problem. You need to upsize your equipment ground if you're reading. This is very important when you have sensitive electronic equipment. Then you note 3, voltage from the chassis, say a chassis of sensitive equipment, whatever. You should read less than 2 volts. And then you shouldn't have any problem with noise and that kind of thing as a rule. So, now that's the general rule. If you wanted, I believe it's chapter 8 in our Stallcup grounding and bonding book, you have about 180 pages of electronic equipment, sensitive equipment, that goes through all of your bonding techniques and grounding techniques, where you're talking from one piece of equipment to another piece of equipment and that kind of thing. Just for you to know that. But 250.4A5 requires an effective ground fault path. 250.4A5, and you can just add in here 250.54. 250.54, and it says you have to have an effective ground fault path, and you cannot use the earth as a path. You know, you have to have that. Now, just to kind of go over what I'm talking about here with you, let's just go back to this first illustration that we looked at and say that you had a 480 volt, 277 volt panel board here, but you didn't have any 277 volt lighting. This happens even today, and it shouldn't. The transformer's grounded, but you don't have any 277 volts, so a lot of times electricians and engineers forget and they don't pull in the grounded conductor because they think, well, we don't have any neutral load. Now you don't have a path for that fault current to travel on, a grounded conductor selected from Table 250.102C1. So the IEEE Green Book and SOAR's grounding book says that this connection to earth ground at the panel, use 5 ohm, and then use 5 ohm back at the utility ground, add 5 ohm and 5 ohm together, that comes up to 10 ohms into 277 volts to ground without a grounding conductor is just about 28 amps if you round up. That's not enough to trip a 350 amp main. So you're choking it. And whatever's grounded out into the facility remains electrified, which could be very, very dangerous situation. So do kind of keep that in mind as you go through these illustrations. And at your leisure time, you couldn't find a better method in going through the 2020 NEC and the 2023 NEC and see how they have updated Article 250 to comply with just what I'm going over with you, except for the rule of thumb methods that I'm giving you. This is something that's been with electricians and electrical engineers for a long period of time, and I'm just passing it on to you. Well, my name is James Grace Stallcup, and I thank you for watching the video. And if you like our videos and you feel like they're helpful to you, hit that subscribe button so every time that we do a video, it'll come directly to you. Again, thanks for watching the video.